A very good morning to everyone. My name is Mriganka Shekhar Chaki. I'm a UNAM postdoctoral fellow at the Unidad Académica, IMAS, Yucatan, Mexico. And first of all, thank you very much for giving me this opportunity to present my talk in the prestigious conference. Today, I'm going to talk about a mathematical analysis of wave scattering phenomena in a reduced Cosserat media with irregular perturbed boundaries. So this particular problem falls in the category of elastodynamic problems. Elastic waves, in particular seismic waves, are of three types: bulk wave, which is a body wave, surface wave, and interfacial wave. A surface wave, again, of two types: Rayleigh wave, which is an in-plane wave, and Love wave, which is an anti-plane wave. If you consider a seismic source, then you can imagine that it hits the epicenter, and then the surface wave generated and propagates through the surface of the earth until it hits the seismic station. And then you again have a body wave, which is a primary and secondary wave that propagates through the earth medium and it hits the seismic station. So if you see a seismograph, you see that the first that hits is the body waves, and then you have the surface wave. But the surface wave are the most destructive ones, which causes the earthquake destructions. Hence, our today's topic is the surface wave. In particular, we discuss the Love wave, which is an antiplane nature, and it has a zigzag motion, and it requires a superficial layer on top of a half space. There another type of a surface wave is the Rayleigh wave, but it doesn't require a superficial layer, and it is an in-plane wave which has a retrograde motion. The Love wave is named after A.E.H. Love, who discovered it. It is not necessary that we have this layered half space configuration with a we always have a planar boundary. There's a possibility that we can have this localized perturbed region, and this region is expressed mathematically in this form, where this Fy represents the geometry of this perturbed region, and we can impose a particular geometry, the known geometry, for example, rectangle, parabolic, or triangular notch-shaped. We deal with this kind of elastodynamic problems by first constructing a mathematical model, which is a boundary value problem. Then we assume a time harmonic solution. Then we eliminate the arbitrary constants by using the boundary condition. Then we deduce the dispersion relation, find the field variable, and then we do the numerical study. The particular material that we're going to talk about is the microcontinuum model, and this particular model is discovered by Engel, and he proposed the question that whether we, in the continuum mechanics, we can consider the atomic molecular behavior or the nanoscale behavior. So you can the idea behind this particular theory is that you have this geometric point in the continuum body, and what if you can consider the interaction between the neighboring particles? So you have this particle which is under the influence of the neighboring particle, which is the much more realistic scenario. And then you have not only the translation, but you have the rotation and also the change of rotation. These are some of the books and references that is related to micropolar media. And I have published this particular paper on this micropolar material with Professor Erimaev, whose book of micropolar mechanics is very famous. The application of the micropolar material is that this type of material in the earth structure can be considered as the geomedium or the heterogeneous structures. The engineering application is the narrow crusher, which brings out the mechanics of the micropolar system. Then you also have magnetic materials. The rotational seismology is particularly we are interested in. Another exciting feature is the metamaterials, which is this periodic arrangement of the structure. And one of the application is the optical metamaterial, where the invisibility cloak is an example of this optical metamaterial. So imagine you put this periodic arrangement of the metamaterials around a particular object, and this electromagnetic wave is coming and it is able to bend the waves. So you do not see this this object. What you see is the background of it. So it's kind of invisible. And you also have the application in the seismic metamaterials, where this Rayleigh wave, the seismic waves coming in, and it bends this wave, and it turns it to a bulk wave. The particular model we are going to study is the reduced Cosserat model, which is a subclass of the Cosserat model or the micropolar model. In the micropolar model, you have the translation and the rotation component, as well as the this grad theta, that is the change of rotation. But we are going to study in this environment where we do not have the change of rotation. So we have the Cauchy stress, which is asymmetric, but we do not have the couple stress. Using this constitutive relation, we can find the equation of motion, where you see that if you consider this alpha to be 0, then we have the elastic wave equation for the isotropic case. The particular structure we are talking about is a layer half space configuration, as we have discussed, and the upper surface is considered to be this rectangle, this perturbed region. So in this case, a love wave is considered to be incident, and it is reflecting from this irregular region and transmitting from this irregular region. So this particular reflection phenomena, if you talk about, then we can consider this displacement component, rotational component, due to this anti-plane nature, like this. So we are able to find for the time harmonic solution the equation of motion, which is reduced form. And we also can find the boundary condition, where the upper free surface is the stress-free condition, where we have this irregularity term here. And at the interface, we have this stress continuity and displacement continuity. For the incident wave field, we can assume these time harmonic solutions in the algebraic form. And using the boundary condition of stress continuity, we can find the dispersion equation. However, for the scattered field, which is in the region of the perturbed boundary, we see that it is not easy to find the scattered fields. So we take the help of the contour integral form, and due to which we are able to find the total displacement field, which is the summation of the incident field and the scattered field, which is in the contour integration. Similarly, we can find the micro-rotational fields, so summation of the incident and scattered field. For the coefficients, we can apply the perturbation method, which is the expansion in terms of epsilons, and we can consider the linear perturbation. So for which, if we put all this back to the displacement component, then we are able to find this type of integral form. If you take a closer look to this integrand here, then we see that it depends on the poles, which is the determinant, making it to 0. And from that, we are able to find the relation, which is a dispersion relation. And this dispersion relation will give us the poles that we need. By calculating the poles, we can define this contour region, which is upper half circle, carefully cutting these branch cuts. And then we can apply the Cauchy's residue theorem, for which we can see that these terms will not contribute when this upper half circle blows up. So we have this summation of the residues, which is calculated here. And using this relation, we are able to find the contribution of the order of the contribution of this integrand here. So if we put all this back to the displacement field, then we see that we have this integral form, and this is still very complicated in the entire domain. So let's focus on the reflected field, which is the left side of the structure. And we see that we have this kind of a region. Using this particular relation, we are able to find the simplified form for the displacement field and for the rotational field. But you see that again, this Fy, which is the irregularity function, is still unknown. So now we can impose the known geometry, that is the rectangle, parabolic, or triangular notch shaped. And for the rectangular shape irregularity, we see that we are able to find an algebraic expression for the displacement and rotational field. For the parabolic shape, again, we can find the algebraic form. And for the triangular notch shape, similarly, we can find the algebraic form for the displacement and rotational fields. We can also validate our theoretical results with the isotropic case, which is a classical, this one is classical love wave equation, dispersion equation. And this one is for the triangular knot shape for the isotropic case, which is given in the paper of Barry Wolf in 1970. We consider some data for the Cosserat material, and we plot the dispersion curve. So we see that in this particular case, the dispersion curve breaks into two parts, and we have this gap. This is a non-propagative region, also known as the bandwidth gap. And due to this gap in the bandwidth, we see that it has application in the acoustic metamaterials, and this paper is important for the application purpose. We also see the discontinuity in the amplitude profile of the displacement component. And if you compare this with the isotropic case, we see that we do not have this kind of discontinuity, and this is due to the critical angular frequency. If we plot all the amplitude profiles for the rectangular shape irregularity, that is the displacement component, and for the rotational component, we see that this discontinuity occurs. If we zoom in particular region, we see that we're studying here the vertical irregularity parameter. We are plotted for the parabolic shape irregularity also, and we see for the triangular knot shape irregularity, and we can see that this discontinuity occurs and it is persistent with all the graphs. So as for the conclusion, we see that all the reflected fields in the upper Cosserat layer are found to be periodic in nature. And the amplitude of the displacement field, for the displacement field, it is much more than the rotational field, which is also expected. The discontinuity reported due to this critical frequency in the amplitude profile, this is not observed in the isotropic case, which I have already discussed. The effect of the vertical irregularity parameter is found to be increasing with the amplitude profiles. We also found that the amplitude for the reflected fields for the rectangular irregularity is maximum, and then we have the parabolic shaped irregularity, and then we have the triangular knot shaped irregularity. And this order is also justified by this geometrical shape, where in the same span how much they occupy the space. In absence of micro-rotational components, we see that all the results that we have found is matched with the isotropic cases. So this particular paper, this particular results are very much important, and it has a huge application in case of metamaterials and its rotational seismology. So thank you very much, and thank you again for giving me this opportunity to present my talk here. And if you have any question, please let me know. Thank you.